Hi everybody, I'm Markus Hecher and I'm presenting my work on Treewidth-Aware Reductions of normal ASP to SAT. Is normal ASP harder than SAT after all? So what is this Treewidth all about? Well, in general, there are lots of problems that are rather hard on arbitrary graphs, but these problems typically become rather simple if we look at the special case of a tree.
Well, and the treewidth now is a way to measure the closeness of a given graph to being a tree or the tree-likeness of a graph.
While treewidth was originally defined for graphs by Robertson and Seymour in a series of papers, nowadays having bounded treewidth k can be seen as one of the most cited combinatorial invariants. In fact, assuming instances of treewidth k renders a large variety of NP-complete problems tractable. We call this tractability fixed parameter tractability since it depends on fixing the parameter treewidth k. In such fixed parameter tractable or FPT algorithms for treewidth, the complexity or the hardness of a given problem is confined to this parameter treewidth. This allows for a more fine-grained analysis where we get polynomial runtime, but in addition the runtime also depends on the value of a function depending only on the parameter treewidth k. In classical algorithm analysis, where we do not have this fine-grained tool, we often only consider instance size and cannot confine the hardness of a given instance to some parts.
There are plenty of these FPT results for several problems. We have single exponentiality for Boolean satisfiability and even counting the number of models of a given Boolean formula. For normal or head cycle free programs, there are algorithms that require slightly super exponential runtime in the treewidth. There are also lots of FPT results for problems believed beyond NP, like deciding the consistency of a disjunctive ASP program. This can be decided actually in double exponential runtime in the treewidth. And now what maybe is a bit surprising is that there are actually frameworks and solvers that apply treewidth for solving problems. On the one hand, they are quite generic frameworks, but even some of these frameworks manage to solve instances up to treewidth upper bounds of more than 200. And then there are even highly optimized solvers for solving specific problems. Okay, but what's the issue then?
Well, as you may have guessed or noticed, the functions in K have a really bad worst case. Well, and if you do not believe in complexity chaos, you would agree that the polynomial f of k is probably not possible. But what's even worse than these worst cases is that there is not much hope to improve these f of k's. So we basically obtain a picture like this. For SAT we have single exponential runtime, which also fits with the lower bound under reasonable assumptions like the exponential time hypothesis. And this also nicely fits the complexity class, because for disjunctive ASP we have double exponential runtime, which is already on the second level of the polynomial hierarchy. Recently we were able to generalize this, where for quantified Boolean formulas of quantifier rank L, it is not expected that one can decide the validity in time lower than L for the exponential in the treewidth, which nicely matches with the complexity, right? Because deciding the validity is on the Lth level of the polynomial hierarchy. So what about normal ASP then? The known upper bound is slightly super exponential in the treewidth, which doesn't fit the lower bound under reasonable assumptions. So can we improve the known upper bound? Can we solve normal ASP in time better than slightly super exponential in the treewidth? No, unfortunately, this is not possible under reasonable assumptions. And that's the focus of this work.
Under reasonable assumptions in computational complexity, deciding the consistency of a normal ASP program is expected to be slightly harder than deciding the satisfiability of a Boolean formula in terms of treewidth. So while SAT can be decided in single exponential time in the treewidth, this is not expected for deciding the consistency of a normal ASP program.
Further, we present a Treewidth-Aware reduction from normal ASP to SAT,
where we only slightly increase the treewidth. This increase is from k to k log k.
Since this reduction is Treewidth-aware, what it actually does, it simulates parts of dynamic programming by guiding the evaluation or the overall reduction along a given decomposition for treewidth. Unfortunately, the increase of treewidth, which is caused by this Treewidth-Aware reduction, cannot be avoided. Let's quickly recap some related work. The exponential time hypothesis, or ETH for short, is a widely believed assumption that is slightly stronger than the assumption p is not equal to NP, and it implies that SAT cannot be solved in sub-exponential time in the number of variables.
The ETH has been used to show conditional lower bounds for, let's say, loads of problems and also for several ones believed beyond NP.
What has been known for a very long time is that positive cycles are responsible for making it hard to compactly represent all the answer sets in a SAT formula. And in fact, there are numerous of these reductions from ASP to SAT. It is also known that there is a relation between formulas of small tree width and small resolution width, which is used for solving the formula. So we hope our insights, as well as the Treewidth-Aware reduction, might be suitable for actual practical use.
This brings us to some preliminaries. Since I guess most of you are familiar with ASP anyway, let's just briefly recap some basics. A program is a set of rules where each rule consists of a positive body, a negative body, and a head.
Negation in this case refers to negation as failure or default negation.
Now, for a set of atoms to be an answer set of a program, first of all, the set of atoms has to be a model of the program, and each atom that is in the model has to be justified or proven. Such a justification is done via level mappings, where each atom gets assigned a level from 0 to the number of atoms minus 1. Intuitively, an atom A is justified. There is a rule with the atom in the head requiring to put this atom to the set M, such that all the positive body atoms have a smaller level than the level of A. So let's now come back to this tree width, or this measure of tree likeness of a graph. Well, in fact, tree width can be defined in terms of tree decompositions.
A tree decomposition of a given graph is an arrangement of the graph into a tree, where each node of the tree, referred to as bag, gets assigned certain vertices of the graph. This has to be done in such a way that the following three properties are satisfied. First of all, every vertex has to occur in at least one bag. In our example here, we see that this is the case for all the vertices of G. Then all the edges have to occur in some bag, meaning that for an edge, the two vertices of the edge have to occur together in at least one bag. Here we see that this is the case for the edge AX, BX, and AB, but we can check that this is true for all the edges of G. Last but not least, we require the connectedness, which basically ensures that if we restrict the tree to a certain vertex of the graph, the result is still connected. In our example, we see that this is the case for C, also for B and for X, and finally also for vertex A and Y, since both vertices occur only in one bag. So this is indeed a tree decomposition of our given graph G. The width of a tree decomposition corresponds to the largest bag size minus 1, which is 2 in our case, and then finally the tree width of a given graph G is the smallest width among all potential tree decompositions of G. Okay, so why do we need these decompositions? Well, we use them for guiding our hardness proof as well as the Treewidth-Aware reduction. But wait, for using a tree decomposition for an ASP program, we need a graph representation, right? Well, the graph representation in our case is quite simple. We use the so-called primal graph or Geifmann graph, which has as vertices the atoms of the program, and we have an edge between two vertices whenever the corresponding atoms appear together in at least one rule. Okay, now we collected everything we need for discussing the hardness of ASP for Treewidth, or for discussing why ASP is indeed slightly super exponential for Treewidth. Okay, so what has been known for a long time is that positive cycles are somewhat responsible for the hardness of evaluating programs. However, in the classical complexity, these cycles are mainly an issue if one wants to preserve all the answer set, and still this only causes a subquadratic overhead. In the parameterized context for Treewidth, while the situation might look similar, the problem is actually a different one. The main issue for Treewidth is that there could be lots of positive cycles which are well spread across the tree decomposition. So in these parameterized algorithms, where we do dynamic programming on top of a tree decomposition, it could be the case that we have lots of cycles and we only see the cycle in parts. It's similar to moving a magnifier along a large cycle, and you're only allowed to look at the magnifier basically, so you only see at once parts of the cycle. Now let's quickly present the idea of the hardness proof. We reduce from the so-called disjoint path problem, which is slightly super exponential in the Treewidth. So what's this disjoint path problem? So an instance of disjoint paths is a directed graph where certain vertices are sources and certain vertices are destination. And our solution to this problem is a set of paths where first of all each source reaches its corresponding destination and the paths have to be disjoint. If you do not have one of these two conditions, the problem is easy. And the challenge now is to actually encode this in ASP, but with only a linear increase of tree width. Okay, so how do we ensure this? The idea is that we guide reachability along a tree decomposition, which we 5 approximate. Such a 5 approximation can be computed in single exponential time in the tree width. The tree decomposition basically orders pairs consisting of source and destination, And it's very important to respect this order, because if you do it in a different way, it could be the case that you completely mess up Treewidth already. So then we link destinations to sources in the order that redecomposition induces. So we make one big reachability question. However, we also need to link destinations according to this induced order. This is done in such a way that if a source reaches an earlier destination, we get a very large unjustified cycle. So there are actually many potential cycles. These cycles are really large, so it's very likely that these cycles are well spread across the tree decomposition. And moreover, these cycles are constructed in such a way that this only causes light overhead in terms of tree width. Finally, we also ensure that every destination vertex is reached, and we do this via reachability atoms for every tree decomposition node as well as vertex. And it's also important that these paths are distinct, so this is also done via this reachability atom. I'm sorry that I can only provide a brief outlook here. I really invite you, though, to read the paper and to ask questions. This now brings me to our reduction from normal ASP to Boolean satisfiability. Okay, so most reductions we have seen so far take an ASP program with n atoms of Treewidth K and produce a SAT instance where the number of atoms is subquadratic. However, the tree width can be really large because there might be rules that are even of size, say, n or log n. While our reduction also causes overhead in the number of variables, this overhead is bounded by the tree width. Moreover, the tree width is only slightly increased compared to the tree width of the program where we started from. Our approach is again guided by a tree decomposition of the normal program, and it uses level mappings for each atom within a tree decomposition node where we have levels from 0 to k-1. However, these levels are not absolute levels but just relative levels, and the level mappings are synchronized between two neighboring tree decomposition nodes. And it is quite important that we guide the justification or provability information of atoms from the leaf nodes towards the root, so the information is guided along the decomposition. So consider a given normal program and the tree decomposition of the program. So we use for each atom a variable, and we ensure that all rules of the program are satisfied. Then we need to ensure that for two atoms x prime of two neighboring tree decomposition nodes t and t prime, if x has a smaller level than x prime in node t prime, then x also has to have a smaller level than x prime in node t, and vice versa. For these local level mappings, of course, we use auxiliary variables per atom and tree decomposition node. Whenever we encounter in a node T a rule where an atom X is in the head of the rule, we actually have to remember if X is proven or justified in node T, which is the case if X is set to true, the body is satisfied, and all the positive body atoms have a smaller level in node T than X. Next, we need to propagate this provability information. So if in a node T an atom X is proven, it is actually proven for T and upwards. If an atom X is proven in a child node of T, it is also proven for T and upwards. Ultimately, we need to ensure that all atoms that are set to true are indeed proven. This is ensured for the provability atom for X and the node T prime where X is removed. If no such removed node T prime exists, this means that the atom X is still present in the root node of the decomposition, and therefore one needs to check this provability for the root node. In the end, the properties of a tree decomposition, as well as the overall construction of the reduction, which means guiding this provability along the decomposition, similar to dynamic programming, ensure that the reduction is correct. However, we do not think that this approach of local level mappings can be generalized such that the answer sets are bijectively preserved. The reason for this belief is that in general it's very hard, given the local relative level mappings, to enforce a unique order. This already brings me to the conclusion. So is normal ASP indeed harder than SAT? Well, you can actually decide for yourself. But what we did here is we showed that at least under reasonable assumptions in computation complexity, as well as for tree width, it seems that already the decision problem for normal ASP is harder than SAT. Then we presented a Treewidth-Aware reduction from normal ASP to Boolean satisfiability, which is guided along a tree decomposition and takes care to only slightly increase tree width from k to log k. It turns out that there is not much hope to significantly improve this increase of tree width. Currently, we are still in the progress of implementing our reductions, and we hope that these reductions might be fruitful for tree width-based solvers. This is also tightly linked to potential runtime improvements, as well as improvements in terms of additional auxiliary variables.
Further, the obvious elephant, namely how can we extend this reduction such that we bijectively preserve all the answer sets and still have the same increase in terms of Treewidth, is still in the room. Okay, so I hope that you had fun watching, and if there are any questions, just shoot. I guess some co-author will answer it. Thanks very much.